We are starting this title. This is Oscillation, and this chapter is famous for SHM. The first concept I'm putting is the introduction for oscillation. What is the main purpose of oscillation?
Oscillation. Main purpose of this oscillation is when these two oscillate back and forth. This means that
You can see that it's a regular to and fro motion about a fixed position, and it's a type of periodic motion. Now, look at this. This is called oscillation. When an object is moving up and down about a fixed point, it is called oscillation. These are the important terms in this oscillation chapter, which you have to revise. One is
time period.
time period. One is time period, and second is
Frequency.
omega is angular velocity. Then we have displacement. And displacement is x. We have the mean position and we have the extreme position. These are the important terms of this chapter. Now, this is called oscillation. Now, a pendulum is swinging between two extreme positions. There is a mean position where the pendulum is at the center. It is called the mean position. And then it swings on both sides. It is called the extreme position. Look, this is a pendulum. It is swinging between the two extreme positions. And when you have the mean position, you will say the displacement is zero. Extreme position is the maximum away it can reach. And for resistive forces, there are different resistive forces like friction at support, air resistance. Now, the first title which has to be explained is displacement. Displacement is the separation of an oscillating particle from the mean position. Now, look at this. At C, at the position C, displacement is x naught. At the mean position, if you consider this point as the mean, this is the extreme position. At the extreme position, displacement is maximum, it is the amplitude. And at the other extreme position, this one, displacement is negative maximum. At the mean position, displacement is zero. And this is a point that is x is equal to x naught sine omega t. Now, in this chapter, what they had done, they had used trigonometric equations. They had used trigonometric equations to simplify the concepts of oscillation like this. Then we have velocity. Velocity, when an object is moving in an oscillation, look, it is the mean position. At the mean position, velocity will be maximum. At the extreme position, velocity will be zero. Now, V's velocity, x is equal to amplitude, and omega is the angular velocity. Now, what is V? V is equal to omega x naught cos omega t. This is the formula. Remember that velocity is taking cos because displacement had taken sine. What's the derivative of sine to cos? If you differentiate, sine becomes cos. Now, at 90 degree, the velocity becomes zero. This is the extreme position. And at the mean position, velocity is omega x naught, which is the maximum velocity. Look at the sketch. This is a cos theta sketch. This is a cos theta sketch at the position A, and position C, velocity is zero. And at position B, velocity is maximum. alternate formula. This is the alternate formula for velocity, which is plus minus omega x naught square minus x square. So at the mean position, x is equal to 0. And at the extreme position, velocity is equal to 0. This is a very important sketch. Look at the shape. It's a circle. Y-axis is velocity and x-axis is displacement. So when you reach the mean position, velocity is maximum. At the extreme position, what is velocity? Velocity is 0. Now comes acceleration. Acceleration is minus omega square x naught sine omega t. This is the formula. Now,
The main position is the
mm,
that is always better towards the main position.
right, and this is the extreme position. Velocity is 0 and acceleration is maximum. At the mean position, acceleration is acceleration is 0. Now, these are two important cases when velocity is 0. Velocity is 0, acceleration will take the usual sign. But when velocity itself is negative, acceleration, negative and positive, changes their sense. Negative A means acceleration and positive A means deceleration. Look at this. Now, this is the master sheet. It shows all the features of velocity, displacement, acceleration on left side and right side. Remember, at the mean position, acceleration is 0. At the extreme position, acceleration is maximum because the object is taking a U-turn. This is the sketch. It's a negative sine theta sketch. It's coming from the lower side. Relation between acceleration and displacement. A is equal to omega square x naught sine omega t. So when you simplify and you put this value, you get a very important equation, which is the main equation of this chapter, which actually controls this chapter. A is equal to minus omega square x. Now it has two possible extensions, one on the mean position where acceleration becomes 0, and one on the extreme position where the acceleration is minus omega square x. This is the gradient line. It is a negative gradients equation, and it means acceleration is proportional to minus x. It's a straight line. Gradient is minus omega square. It's a very important sketch, appeared many times in the paper. Then comes simple harmonic motion. This is the core idea of this chapter. What is simple harmonic motion? It is the main idea is oscillation. It's a type of oscillation in which the displacement from the mean position is directly proportional to the acceleration and is always directed towards the mean position. So this is the displacement, and look at the relation. A is proportional to minus x. So what's the core idea? SHM, simple harmonic motion. Simple harmonic motion is actually a type of oscillation where acceleration is proportional to negative displacement.
Displacement is always affected towards the main position.
And acceleration is always directed towards the mean position. Look at this. Acceleration is always directed towards the mean position. Now look at the examples of SHM. For example, a loaded vertical spring, and we have a spring with its original length. We put some load on the spring stretches out, and then the spring is now gently pulled out. If you pull the spring gently and then you release, what will happen? If you pull the spring down,
it will oscillate back and forth.
It will oscillate up and down. Now the spring is gently pulled further down and released. So it will be following this type of oscillation. Now look at this. And now if you release the spring from this position, Now, mg is equal to ke. What is k? K is the spring constant. So when you pull it down, you will get this formula. A is equal to minus k upon mx. So when a spring is loaded, it's moving up and down. It is actually acceleration. Now, this is a little derivation which shows that time period of a oscillating spring is how much? T is equal to 2 pi under root m upon k. Remember that SHM main equation is this, and this is the equation for this particular situation. Horizontal oscillation of a mass. This is a mass, and look, this mass is oscillating like this.
Okay, sir.
What is this? This is called horizontal oscillation. This is the mean position. It goes in, so it is extension minus x. And when it goes out, it is extension plus x. Then look at this graph. It is acceleration is proportional to x. So F is proportional to x. Now area, look at here. Area shows the work done. So work done is equal to half kx square. A is proportional to minus x. Horizontal oscillation of a mass between two springs. Look, this one. Now, this is a mass between the two springs, and look, it is moving like this. One side it compresses, other side it stretches. One side compresses, other side stretches. Now, this is the central position. Then it goes on the right, and then it comes to the left. Now, this is the formula for combined extension. And as acceleration is always minus proportional to minus x, so omega is under root k1 plus k2 upon m. Now look at this molecular vibration in solid. This is an example. Energy considerations in oscillation. So in any oscillation, total energy always remains constant. Total energy always remains constant. Look at this. It's moving, it's swinging, and potential energy converts to kinetic. Look at the mean position. Potential is 0 and kinetic is maximum. At the extreme position, potential is maximum and kinetic is 0. So when a pendulum is swinging, when it is at the maximum position, this is the object oscillating. When an object is oscillating like this, when an object is oscillating like this, it has a total energy. Total energy is K plus U. What is K? K is the kinetic energy and U is the
Potential energy.
U is the potential energy. So when you talk about kinetic energy, it is half mv square. So we replace this formula for V and we get another formula for kinetic energy. Look at this. This is the formula for kinetic energy. At the mean position, kinetic energy is half m omega square x naught square. And at the extreme position, kinetic energy becomes 0. Total energy. In order to find the total energy, we use the translation that total energy is K plus U. At the mean position, potential becomes 0 and kinetic is maximum. This maximum kinetic is equal to K maximum. Kinetic maximum, it's a this is the maximum EK. Now, if we take the mean position, our potential is 0. So the maximum kinetic energy becomes equal to total energy. This is the formula for total energy. What is potential energy? Potential energy is capital U. It is a stored form of energy. How we find potential energy? What we do, we take the same formula. We know the total energy. We know the kinetic energy. We put them and simplify them. So we get a U. What is U? Half m omega square x square. A very important sketch. The smiley face shows potential energy. The sad face shows kinetic energy. And you can see the energy is translating. So the horizontal line is showing total energy. The first graph shows potential, second graph shows kinetic, and the line which is horizontal is called total energy. Damping. What is damping? Damping is the resistance to
of the oscillation.
Damping is the resistance to oscillation. And resistive forces are friction, air resistance, any fluid resistance, etc. There are three types of damping: light damping, critical damping, and heavy damping. What is light damping? Light damping is defined as the damping is not very high, not very low. It is not stopping the object. The object does not stop. So energy decreases, amplitude decreases, but the time period does not change. Look at this. This is called light damping. Look, the amplitude is decreasing. And then comes critical damping. Critical damping is what? In critical damping, the object is allowed to oscillate shortly, but forced to stop at the mean position quickly. Just like the suspension system of vehicles, car suspension system is critically damped. So when a jump comes, when a breaker comes, it moves slightly up and down and stops. This is a moving coil meter. It is also critically damped. So the system quickly regains the equilibrium. It comes back. What is heavy damping? If the damping is so high that the object does not return to its equilibrium position, this is the case when object stops somewhere, like a compass. Look at this. This is a compass. It is heavily damped. So there is a screw. You tight it. The compass now cannot oscillate. Examples of damping. This is a magnet, and this is an electromagnet, but there is no power here. When you oscillate the magnet and when the magnet goes in and comes out, what happens? The meter needle, this needle vibrates. Why the needle vibrates? Because the magnetic flux from the magnet is cutting the solenoid. This is an example of electromagnetic induction. What is resonance? Resonance is an extreme condition of oscillation. Resonance is an extreme condition of oscillation. Everything has a natural frequency. For example, this is the frequency of a simple pendulum. Now you give it an impulse, the object begins to oscillate. This is the frequency, driver frequency. Now you increase the driver frequency by giving impulses, by giving short impulses, and driver frequency becomes equal to natural frequency. Amplitude becomes maximum extreme condition. So when the driver frequency becomes equal to the natural frequency, what happens? Amplitude becomes maximum, and this extreme oscillation is called resonance. Amplitude is related with intensity, and intensity is a measure of energy. So what happens when resonance occurs? System absorb energy from the surrounding. A very important sketch. We have heavy damping, so amplitude is small. You do the light damping, amplitude increases. Then you do further that, you release the damping, remove the damping, resonance occurs. This is called the natural frequency at which oscillation becomes extreme. So in some cases, resonance is good and some is bad. For example, this is a microwave oven, so resonance is good. This is a MRI, resonance is good. Earthquake is a dangerous issue of resonance and a dangerous effect of resonance. There are some factors which control the resonance: degree of damping, natural frequency, structure of substance. Normally, damping opposes resonance. So the most common prevention of resonance. So resonance can be prevented by damping. This is the washing machine. So if you put a heavy mass in the center of the drum, resonance occurs. Now this was our revision for SHM.